when rocks deform, they squeeze on the pore volume and change the pore volume. This will change fluid pressure, and changes in fluid pressure can drive fluid flow. And as fluids move through a porous material, the pressure will change. This can cause the rock to deform. And it's through these interactions that fluid pressure and rock deformation can be coupled. One example is illustrated here. We're looking at the ground motion on the bottom produced by an earthquake recorded by a seismometer. In this case, the earthquake is 3,000 kilometers away from the seismometer. In particular, we're plotting the ground velocity, the speed at which the ground is moving up and down, which is proportional to the volumetric strain. And you can see the arrival of seismic waves. On the top is the water level in a well located right next to the seismometer. And you can see that water level also goes up and down. It mimics, in fact, the volumetric strains, the ground displacement. You might also notice the amplitude of these ground motions are quite big. This is about 1.5 meters from an earthquake over 3,000 kilometers away. Today I'm going to describe the simplest, provide the simplest description that couples fluid properties, fluid pressure, and deformation of rocks, called linear poroelasticity. But in fact, linear poroelasticity, coupled to a fracture intersecting the well, can quantitatively transfer this deformation to that water level over a wide range of frequencies. You might also notice that after the passage of seismic waves, there's a permanent change in water level. It's only about 10 centimeters. This is something that cannot be explained by linear poroelasticity, and in fact is the subject of active research. And last, let me remind you, if you have any questions at any time, just interrupt and ask, and I will adjust what I say and how I say it based on feedback or questions as we go. So I'd like to begin with some observations to motivate the development of these simple ideas. First, it's been long noted that water level in wells is correlated to tides, solid earth tides produced by the sun and the moon. Here's one example. In green, on the vertical axis is the volumetric strain, is the strain or the deformation produced by solid earth tides for a 1-week period on the horizontal axis. In blue is water level in a well, and you will notice that water level more or less tracks the deformation. Any other interesting signals, though, or differences between these two curves? Yeah. There's a very small shift. In fact, water level peaks a little bit before the deformation. We'll return to this quantitatively later. Anything else? Yeah, well, the amplitude, of course, the scales are on different axes and have different units, so it's somewhat arbitrary. Yeah, so tides does not explain everything we see in the water level. There are other hydrological processes that are changing water level here. Okay. Next observation are changes in water level as surface loads change. In this case, we have a train pulling into a train station. Time on the horizontal axis in minutes, water level in a well, train pulls into the station, water level rises. The train stops and water level gradually decreases. Train departs from the train station, water level goes down and gradually recovers. Okay. And we'll return to this example quantitatively later as well. And questions, Olivier? No? Okay. Yeah.
Just a remark, we have this same behavior in the Barcelona field site, where there is this experimental site, so I don't know where are the Barcelona people, but we have one here, but another student also. Yeah. Anyways, we see this behavior when the train is passing, and also we have the waves of the sea just close by, so we have a mix of signals.
These are very useful signals because using the models we'll be talking about next, you can extract information about hydrogeologic properties from these kinds of signals, both permeability and various elastic properties. Okay, next example is that the ground surface moves up and down as we inject or remove fluids from the earth. I'll show you just one example. We're looking at an oil field in Texas, this little box right here in Texas, magnified here on the right. The contours you see here show ground displacement. Actually, it's velocity of the ground moving in millimeters per year. And you'll notice ground is moving up quite rapidly. This is several millimeters per year. These squares that you might be able to see are the location of wells into which wastewater is being injected. The colors of these different squares corresponds to the injection history plotted on the bottom. Right, so the red injection is occurring over here. It's the biggest. there's an interesting correlation, right, between how much fluid is injected and the ground displacement. Over here, where the injection rates are the biggest, we see very little ground displacement. Over here, the water's being injected quite a bit deeper. Okay. I'll return to this example later, but it also turns out that where we have lots of ground displacement from the shallow injection, we have no induced earthquakes. These little circles you see are earthquakes, presumably induced by that fluid injection. Okay, next example, which I will not show a figure for, is that sometimes after you start pumping water out of a well, nearby monitoring wells will show an increase in water pressure, water level. That's the opposite of what you should expect, right? If you remove water from a well, pressure should go down, water level should fall. And this is an elastic effect. When you remove water from a well, there's an instantaneous elastic deformation that compresses rocks, increases fluid pressure, and on very short timescales, you see a rise in water level. And the last example is the triggering of earthquakes by, for example, filling reservoirs, or also injecting water underground, like the example I just showed you. I think this was first clearly documented by the filling of Lake Mead in 1935 on the Colorado River. Okay, this is a picture of the reservoir. Here's some data. There are two vertical axes here. We'll start with the smooth curve. Horizontal axis is time in years. And on the right is water level in the reservoir. And you can see water level rising after the dam is constructed by about 100 meters. It's a pretty substantial reservoir. This gives rise to a surface load of about 1 megapascal. The histogram with scale on the left is the number of earthquakes that occur. This point goes off the graph by about a factor of 2. And you can see that as water level rises, the number of earthquakes increases. Injecting water underground or fluids underground can also induce seismicity. This was first clearly documented at the Rocky Mountain Arsenal waste injection site. The biggest of these earthquakes was a magnitude 5.2 earthquake. Plot on the top is the volume of fluid injected as a function of time, and on the bottom is the number of earthquakes that were triggered. Okay. So what we're going to do is introduce the simplest description that couples deformation to fluid pressure. And there are two basic phenomena we need to address. First, how are solids coupled to fluids? And here we're interested in how stress changes will cause changes in fluid pressure. And then the opposite, how do changes in fluid pressure give rise to deformation of solids? And so we're going to address three questions. How are deformation and fluid pressure coupled? How do we couple deformation to the fluid flow? And then what can we do with the understanding? And hopefully I've already addressed this last question through those kinds of examples, There are lots of equations that describe ultimately the relationships we will look at. And so to save some time and not take you through tedious derivations, I did type up the equations behind what I'll be showing you. I think most of you probably got them by email. And there are lots of equations. If you have any questions or you find typographical mistakes in equations, do let me know. If you didn't get a copy of those notes, just let me know as well. There are many books that provide a description of the coupling between deformation and fluids. We saw this in the previous talk for the case of fractures. I'll just highlight one book by Herb Wang. And this book does provide a nice historical perspective in addition to deriving the equations. Okay. So we'll start with the simplest description introduced by Biot in 1941. This was an influential paper. At the time I typed up the notes, it had been cited 8,600 times. Okay. And so let's begin with some of the assumptions we will make as a starting point. We will assume our rock is saturated, all the pore space is filled, and it's isothermal, so we don't have to worry about changes in temperature. We're going to assume that the stress and fluid pressure are our independent variables, and we are going to be interested in two quantities. What is the deformation of the rock, and how is the amount of fluid inside that rock changing? Okay. The amount of fluid in the rock I'll call, denote with the symbol F. I'll call it the fluid content, and it's the fluid mass in the rock divided by the volume of the rock and its fluid density. So it's a dimensionless number you can think of as being a measure of the amount of fluid in the rock. Okay. So this means with these being the independent variables, our strain, epsilon, will be a function of the stress and the fluid pressure. The fluid content will also be a function of the stress and the fluid pressure. And so Biot introduced the equations written on the bottom that say that the change in stress is proportional to the change in strain is proportional to the change in stress times a constant plus another constant times the change in fluid pressure. And similarly for the change in fluid content. So now we can understand why this is called linear poroelasticity. 3 words, linear. Why linear? We're assuming the strain and the fluid content are linearly proportional to the stress and the pressure. Elasticity, linear elasticity assumes the stress is proportional to the strain, right? And the constant of proportionality is the spring constant, right? That's Hooke's law. And where does the poro come from? We've simply added a fluid pressure to that description. Okay, so the meaning of the expression linear poroelasticity hopefully is reasonably straightforward. Okay, so you'll notice that we have these partial derivatives that tell us how volumetric strain scales with stress or pressure, or fluid content scales with stress and pressure. And these define 4 constants, and we're going to call them constants because we're assuming a linear relationship, and they're rewritten here. And so we're pretty much done. This is all there is to say, except that we can imagine a representative elementary volume that we're interested in. The boundary conditions may be variable. And so as a consequence, in fact, the relationship between deformation, stress, and fluid pressure can be a little bit more complex. In Biot's paper, he points out why 2 of these constants are equal to each other. I'll just explain briefly in words the basis for this argument. I'll refer you to the notes for some details. He introduces a potential, and you can think about this as something like an energy that has 2 parts. There's an elastic strain energy and an energy associated with the fluid compression. And so if you assume that this potential is the sum of those 2, then there's symmetries in these 2 different derivatives that allows H and H1 to be the same. There are a variety of different ways to rearrange these equations to obtain different poroelastic constants. 2 of the most commonly used ones are called Skempton's coefficient and Biot-Willis coefficient, and they can be related to the 2 of the Biot coefficients. Skempton's coefficient, these have physical meaning. All these poroelastic constants mean something physically. For example, the Skempton coefficient will tell you how much fluid pressure will change as you change the mean stress for the case where the amount of fluid inside the rock does not change. If we take a rock mass and don't let the fluid mass change, we call that undrained conditions. The fluid is not moving. Okay. So under undrained conditions, as we change fluid, we're interested in how much fluid pressure might change as we change the stress. And this is a number somewhere between 0 and 1. The Biot-Willis coefficient tells us how much the fluid mass changes as we deform the rock, for the special case that we're not letting fluid pressure change. Okay. For many problems, we're interested in how much the fluid content changes as we change fluid pressure, right? In standard hydrogeology equations, you're probably familiar with things called storage properties or specific storage. And the value of these storage properties will depend on the boundary conditions that apply to the representative elementary volume. For example, these storage coefficients are always a change in fluid content with respect to pressure, but under different conditions. For example, conditions of constant stress or constant strain. And we obtain different expressions for these values. Okay. At the end, I'll come back to explain why this matters. And the derivation of these expressions are in the notes, so I'll save time by not going through it. But by introducing these different forms of, or different expressions for the poroelastic constants, we can obtain different constitutive equations. Again, constitutive equations relate strain and fluid content to stress and fluid pressure. And so I've written down alternative forms here in terms of the Biot-Willis coefficient and the Skempton coefficient. The bulk modulus, K, describes the relationship between stress and strain at constant fluid content. But we can also imagine measuring it, for example, in the case at constant fluid pressure, under the case where we're not letting fluid move in and out of the rock. And so we will call this the undrained bulk modulus. And the undrained bulk modulus is related to the normal bulk modulus you might measure for a rock and some of these poroelastic constants. Okay. So rearranging these equations, we can also now obtain a physical understanding for what it is that gives rise to strain in rocks. And the strain in rock is proportional to the stresses that are applied, the elastic deformation that depends on the undrained bulk modulus. And there's a second contribution to deformation that arises from changes in fluid content, and the Skempton coefficient would be that constant of proportionality. Question? No? Okay, so the point is, by rearranging these equations, we can try and understand the origin of changes in fluid pressure, the changes in strain, and there's always an elastic component and a change in fluid content. Okay. This is the basis for using water wells, for example, to measure strains inside the earth. So going back to the equation from the previous slide, we can rearrange it to get the change in pressure, which is something we can measure in a well, and there's a contribution from the change in strain and from the change in fluid content. If we assume there's no change in fluid content, we have undrained conditions. This term goes to 0. And so we can relate the strain to the water level changes we measure. And there's some constant of proportionality here, these poroelastic constants. This also allows us now to introduce this concept of effective stress that was described in the previous presentation by Caroline. Right? So going back to Biot's formulation, we have a change in strain related to a change in stress and a change in fluid pressure. I can define a new definition of stress, we'll call it an effective stress, that combines the change in stress and the change in fluid pressure times a Biot-Willis coefficient. Okay. Let me do something else quickly in case this is not familiar. Our stress tensor is illustrated here, and in our original coordinate system, we have normal stresses and shear stresses. For any stress tensor, we can find a new orientation where there are no shear stresses and just normal stresses. Those are what we call the principal stresses, and the convention is usually such that sigma 1 is the biggest, sigma 3 is the smallest. Okay. Okay. So I'm going to, I had this list of observations that motivate what we're going to be talking about today. I'm going to try and remember to go through systematically all of these. Yeah, Antonio?
It's possible that during geophysics or engineering, there is two different formulations for stress. Either you assume the stress are negative for compression or positive for compression. In your case, I guess you're assuming that they are negative for compression.
No, I think for what I'll be showing you on the graphs, compression will be positive.
The strain compression or the stress compression? So that's quite tricky sometimes when you read different papers from different backgrounds.
So I guess geologists and engineers often use different sign conventions for stress, whether positive or negative is compression or expansion. I don't think it'll matter for what we do here, but we'll see. If it becomes relevant, just ask me again. Okay, so let's try and understand how it is that filling reservoirs induces earthquakes. Okay. And we saw this in the previous talk, right? The relationship between stress, shear stress, and normal stress, and when we get failure, right? So we've oriented our coordinate system such that our biggest stress is vertical, the smallest stress is horizontal, and in this rock we have a surface of some orientation with angle theta relative to the smallest stress. And on that surface, of course, we can compute by projecting those principal stresses onto that surface. What is the normal stress and the shear stress? Okay, this is the failure envelope that was described in the previous talk that relates the shear stress needed to initiate motion on a surface as a function of the normal stress. The intersection here is the cohesion, and the slope is often called a friction coefficient. Okay. And this circle that you see plotted here, as in the previous talk, simply shows the relationship between the normal stresses and the shear stresses on surfaces of any arbitrary orientation, whereas we move away from sigma 1, this angle right here is 2 times the angle from sigma 3. Okay, so how is it that we're going to get failure on faults or on surfaces? We need to get this circle, right, some combination of shear and normal stresses to meet the criteria needed for failure. So what's one way we can, are we going to get failure for the case illustrated here? No, right, because we haven't intersected our failure curve. So what's one way we can get this rock to break or fail? Yeah, we can make sigma 1 bigger. Luckily, this is the first example in this animation. Thank you for making my life easy, right? So we just make this stress bigger, the circle gets bigger, eventually we get failure, right? This is the example of filling a reservoir, right? When we fill a reservoir, we're making the vertical stress bigger, right? And then we can get failure. Whoops, what's the other? Yeah. We can make sigma 3 smaller, essentially we're pulling outward, right? And so again, we're making the circle bigger so that we intersect the envelope. What's another way we can make failure happen? Yeah, we can increase the fluid pressure. If we go back to that concept of effective stress, and since I've been talking so slowly, this was a few slides ago, right, we can subtract from the stress that Biot-Willis coefficient times the fluid pressure. That's removing from each of these components the same amount of stress, and the circle will move to the left. Right. And physically about what is happening here, by changing the fluid pressure, this fluid pressure is pushing out in all directions, lowering the effect of normal stress, so the same amount of shear stress can initiate failure. And this is the way in which fluid injection presumably can induce failure, right, by changing fluid pressure. Okay. As far as I know, this was first described in applications to geological problems by Hubbard and Ruby in 1959. They were trying to understand how you get these very long, low-angle faults, for example, in the Rocky Mountains in the western United States. And in this paper, they describe an experiment done with beer cans. And I recreated this experiment in my lab. These are 2 Coke cans, they're not beer cans. And let me describe what this experiment is. This is a flat surface. These cans are empty. I removed all the liquid. I turned them upside down. The one in the foreground was put in a refrigerator. The one in the background is at room temperature. Okay. What I'm going to do next is lift up this glass. And as I lift up the glass, what is happening to the stresses between the can and the surface? What's happening to the magnitude of the normal stress as I change the angle? It's going down, right? The component of the stress perpendicular to the surface is decreasing. And what's going to happen to the shear stress? The downslope component will get bigger and bigger as we make the slope bigger, right? We're simply projecting the force of gravity onto a surface whose orientation is progressively changing. And maybe to go back here, right, we're essentially making the shear stress bigger relative to the normal stress. The normal stress is going down, the shear stress is going up. Okay, I hope this works.
And is the idea of cooling the cans, do you want to talk about that or not?
Well, let's see what happens. No. This is very disappointing because I made this movie so he didn't have to do the experiment. Maybe at the end I'll show it this afternoon to start. This can slides at an angle of about 2 degrees, the cold one. The warm one slides at an angle of about 45 degrees.
So is it because of condensation on the surface of the can?
Well, but why would that matter?
I don't know, you get fluid at the interface.
Yeah, okay, so actually in both cases, I made the bottom of the can wet so that they're in contact with the glass.
But the cold one heats up, and that means it expands.
Yeah, exactly. The air inside the cold can warms up when it enters room temperature. As gases warm up, they expand. That increases the pressure. It decreases the effect of normal stress. And so the shear stress needed for failure is much smaller. Let me try one more time.
Do you have the video on your computer?
But I don't know where on my computer. Do I have to know what it's called?
It's part of, yeah, so part of the main fragment. On the top. No,
Do I do this?
yeah,
And what do I call it?
what's the name of the video?
I don't know. I'll look for it later and figure out where it is. Okay. This afternoon, we may or may not have a discussion about induced seismicity, depending on whether or not we have student presentations. Induced seismicity are earthquakes presumably caused by engineering our environment. Both plots that you see here show the number of earthquakes in Oklahoma with magnitude bigger than 3. Oklahoma is a state in the central United States as a function of time. And you can see a very large increase in the number of earthquakes. The inset is simply a logarithmic scale. And the biggest of these earthquakes was a magnitude 5.8 earthquake. And these are presumably induced by injection of wastewater, changing fluid pressure, and allowing failure to happen. So going back to the example I showed you earlier in Texas, where we saw the large amount of surface uplift from shallow injection, very little surface uplift from the deep injection. From the surface deformation, this is measured by INSAR. We can invert this to determine the volumetric strains in the subsurface and the changes in fluid pressure. Okay. What's plotted on the left with the colors, it's sort of an attempt to show a three-dimensional illustration of where these volumetric strains are happening, is the volumetric strain. On the right, the computed pore pressure from known elastic properties. And for the deeper well, where we have very little surface deformation, we have much larger fluid pressures. And the little symbols you see here, color-coded by the time of the earthquake, show the induced earthquakes. They happen at shallower depths and progressively migrate deeper. Presumably, this is an example of changes in fluid pressure inducing seismicity. There are other ways, of course, to induce seismicity. We talked about those three different ways to initiate earthquakes, one by changing surface loads or by changing fluid pressure. The example we just looked at in Texas or in Oklahoma is thought to be caused by changes in fluid pressure. In this little comment in Science this year, they also note that extraction of gas may allow the vertical loads to be transmitted to faults, initiating failure as well. So the example we just looked at, you may have noticed, we assumed stress was a single number. Stress was isotropic. In general, those stress need not be isotropic, and so we can rewrite our constitutive laws for the anisotropic case, right, for the different components of stress. And so I've done this here for you. Let me just define some of these variables. We haven't seen, I think we saw nu in the previous talk. E is a Young's modulus, and so it transfers, it tells us, given a certain amount of stress in one direction, what is the strain in that direction? The Poisson ratio will tell you how much deformation you have in a direction perpendicular to that applied stress. Okay. And here's the Poisson ratio nu. So very similar to the equations you saw before that related the strain to this change in stress and the change in fluid pressure. Now, of course, we have shear stresses, so we have a shear modulus as well. Okay. And so we can rewrite these in index notation. It's way more efficient on the right. So now we have many more poroelastic constants because we have many different types of boundary conditions that can apply to our representative elementary volume. And so some of the different conditions that might apply to different problems are illustrated here. We talked about the concept of drained and undrained. When we talked about undrained before, that was the case where as you deform a rock, you're not changing the amount of fluid inside the rock. Drained would correspond to the case where as you deform the rock, there's no change in fluid pressure. And in general, of course, things should be anywhere in between drained and undrained as you deform a rock. There's also a condition called unjacketed, where there's some mean applied stress. We assume that that is equal to the change in mean applied stress is equal to the change in mean fluid pressure. Okay. And so we can evaluate compressibilities. Compressibilities describe changes in volume with respect to pressure under all these different conditions, whether we let the fluid whether it's unjacketed, and so the mean stress and fluid pressure are the same. We can evaluate the compressibility of just the pore space, or we can assume there's no change in fluid pressure, and we also saw the case where it was undrained. And the important thing that I go through in the notes, I suppose, is that all these different expressions for compressibility may apply to different circumstances you're interested in, but they can always be written in terms of some of the other more commonly used poroelastic constants, right, which were things like the compressibility of the fluid, the Biot-Willis coefficient, the Skempton coefficient, and the porosity. Okay. So again, going back to our storage properties that tells us something about change in fluid content as we change fluid pressure. For the anisotropic case, right, before we just had we could either change the stress or fix the stress or the strain. But for the anisotropic case, we can have mixed boundary conditions. A commonly used one is the specific storage, where we assume there's no change in vertical stress and no change in horizontal strains. Right? And it's because we have all these complex boundary conditions that apply that we have so many different poroelastic constants. Okay. Let's see. So we can also measure some of these using measurements we make in wells. Right? For example, if we had a well located next to the ocean, and as the ocean level goes up and down, that's a load applied to the surface of the Earth that's going to compress aquifers and change water level in wells. Right? And so we can measure the change in water level, which tell us about change in pressure, as we change the surface load, assuming no horizontal motions and undrained conditions, no change in fluid content. And this is often called the tidal efficiency, which we can express in terms of these various poroelastic constants. Another way to load the surface of the Earth is by changing atmospheric pressure. As we change atmospheric pressure, that's a force that is applied to the surface of the Earth, which will compress or uncompress aquifers. Water levels will go up and down. But it's a little bit more complicated because that change in atmospheric pressure is also affecting the water in the well itself. Right? The atmospheric pressure will make the water level in the well go up and down, and there's a contribution from deforming the aquifers. And so this is called the barometric efficiency, and it's 1 minus the tidal efficiency. This is something that's easy to measure. Here's one example where I'm plotting on the vertical axis, let's see, with the thin curve, water level. The bold curve, the thick curve, is changes in atmospheric pressure. And you can see they look like mirror images of each other. Right? By dividing the atmospheric pressure by density and gravity, we can convert this to an equivalent water height. The ratio is that barometric efficiency right here, which tells us about this quantity gamma, which we can relate to poroelastic constants. So this is one way in which we can use natural observations to measure these different properties. Okay. So second thing we want to do today is understand, so we just talked about how deformation changes fluid pressure. How does fluid pressure couple to flow? So I wrote down here an equation for conservation of mass. I think we've seen this many times over the past 2 weeks. It relates the change in fluid content to the flux of fluid out of our volume, plus any sources or sinks. In a porous material, we know what the flux is. It's governed by Darcy's law. And so we have a differential equation that relates changes in fluid content to the Laplacian of the pressure, if we assume permeability is a constant, and any sources or sinks of fluid. Now, for the special case where we have no change in surface load and no horizontal strain, the storage property that tells us how fluid content changes with pressure only depends on pressure. This was the specific storage. In that special case, we can relate the change in fluid content to the change in pressure. I dropped the D's here. And we obtain the standard equation used for often used in hydrogeology that describes the evolution of fluid pressure. This, though, only applies, of course, under very special conditions, right? Boundary conditions. We have conditions on the stress and the strain. In general, right, we know that the change in fluid content now from linear poroelasticity depends not only on the change in fluid pressure, but the changes in mean stress as well. Okay, so we can use this more general expression in our conservation of mass equation. And we see that we have an additional term that relates the changes in stress with respect to time to the evolution of fluid pressure. And I suppose one way you can think about this more general equation is that this is your standard groundwater flow equation, and the change in stress with respect to time looks like a source or a sink of fluid pressure. So we can revisit the train example we saw before. At very short time scales, there's no time for fluid pressure to move. The change in stress gives rise to a change in pressure. Right? This change in stress is from the weight of the train. And that explains the initial rise in fluid pressure. Train pulls into the station. This term goes to 0 because we're not changing the stress with respect to time. Pore pressure can diffuse, and that explains the gradual decrease. When the train pulls away, this first term again becomes large, and we see the opposite. So I'd like to end by taking you through one example of how we couple these. And the example we'll look at is how we can use the response of water level in wells to the periodic deformation produced by solid earth tides to probe conditions in the subsurface. And this was first done by Paul Shea and co-authors in 1987. I'll take you through their analysis. A little bit about the geometry and boundary conditions. We have an aquifer that's open to a well. We'll assume only horizontal flow. The aquifer is isotropic and homogeneous. And the well radius where water flows in and out of the aquifer has one radius, RW, where we're measuring water level may have some different radius we'll call r subscript c. And the difference between these two radii matters because of conservation of mass. Okay. And the last thing what we're going to do is this aquifer is going to compress and uncompress from the tides. And that's going to cause flow to go in and out of this well. Water level is going to go up and down. And S will describe the drawdown of the water level or the hydraulic head relative to some reference condition. Okay, so we can write down the governing equation for this problem, illustrated here. S and T are proportional to specific storage and hydraulic conductivity multiplied by the aquifer thickness. Right? And so T is often called the transmissivity. Notice they appear here together, right, in combination. That's often called the hydraulic diffusivity. And this is in a radial coordinate system. And so we have, in fact, in writing this down in this form, made some assumptions, right? No change in vertical stress, no horizontal strains. Okay. So these two parameters, the hydraulic conductivity and storage, appear together, right? But our boundary condition for the flow, the flux into the well, only depends on the transmissivity. And so this is going to allow us to separately determine the storage properties and the hydraulic conductivity, or the permeability. Okay, we're going to apply periodic or harmonic forcing. This is a linear differential equation. Because this is linear, right, with a periodic forcing, our solution will also be periodic. And so we can assume that is to help us find a solution. And I'm not going to take you through the details of how you do this, right? But this is differential equations in cylindrical geometries usually have Bessel functions as the basis function. And so our solution is going to look like the sum of some Bessel functions. Okay. And so this is what these things called Kerr and Chi are. They're Bessel functions of order 1. But you will, alpha, maybe I should go back. This is a standard diffusion equation, right? And you make diffusion equations dimensionless by taking a hydraulic diffusivity. Diffusivity, time, and length are always scaled with each other. Right? And so we can have a dimensionless variable that relates our hydraulic diffusivity to the period of the forcing. That gives rise to a length scale. And so our solution will depend on that length scale, diffusion length scale. And we've separated, and notice our hydraulic conductivity and our storage properties always appear together here. But because our boundary condition for the flow only depends on hydraulic conductivity, we've separated out also the transmissivity. So we can look at the amplitude of the forcing from the tides compared to the amplitude of the water levels. I'll call that A. There's also a phase shift in this problem. I'll call this eta, that depends on the transmissivity and the storage properties. And so I'm going to show you the figures from the original paper by Paul Shea to just make a couple points. On the vertical axis is the phase shift. This is the time between the peak water level change and the peak tidal forcing as a function of the transmissivity made dimensionless for different values of the storage property on these different curves. And a couple things you will notice. The solution, the phase shift, is much more sensitive to the transmissivity or the permeability than it is to the storage properties. Right? The storage properties here are changing by 4 orders of magnitude. Transmissivity is changing by only a couple orders of magnitude. The amplitude of the response similarly is much more sensitive to the transmissivity than the storage properties. And so what you can do here is by monitoring water level in a well, you can in principle back out what the transmissivity of the well is. And if your measurements are accurate enough, you might also say something about the storage properties. The example I just showed you was for horizontal flow in and out of an aquifer. You can imagine there are cases where the flow is predominantly vertical, up and down towards a free surface. And you can similarly derive an equivalent expression. And I've written it down here. It's in the notes, so I won't go through it. Okay. So this is in principle straightforward, right? If we know what the tidal deformation is, we can measure the water level. But tides are more complicated because there are many bodies in our solar system. And so here's a list of all the different tidal forcings and their frequency. They're illustrated graphically on the right. M2 is the tide produced by the moon. It's the most commonly used. So these are the different components, or different tidal components. On the bottom is the sum of all of these, what we actually measure. The most commonly used for this type of analysis is the M2 tide. Why? It's not exactly 12 hours. At 12 hours, you see all kinds of other things that contaminate your signal, like the difference between day and night, atmospheric pressure changes that are typically a 12 hours period. The moon has the biggest gravitational effect on the Earth, so it's also the biggest of these signals. And so in practice, to do this tidal analysis I'll be talking about, you have to separate out the different tidal components in your signal and analyze them separately. So I'll show you one example very briefly with a bit of detail. On the top is water level measured in a well. You can see some long period fluctuations here. These are probably from atmospheric pressure changes. And you can see the tides down here on the bottom. This is a 2-week time period. Okay, on the bottom is the atmospheric pressure. Okay, the next figure shows the power spectrum of these fluctuations. A power spectrum shows you how much variability occurs as a function of frequency on the horizontal axis. Okay, so let's see. The red curve is the atmospheric pressure variations. The water level is shown in blue. And you can see that the blue and red curve kind of look like each other, but they're offset a little bit. And that offset tells you something about the barometric efficiency, how efficiently are pressure changes coupled to atmospheric pressure changes coupled to pore pressure changes. Okay, so with the barometric efficiency of 0.55, we get the green curve, which matches these very long period signals. And then you can see at higher frequencies are tidal forces, or tidal periods, O1, K1, S1, M2, S2. We have fluctuations in water level as well. Okay, and what we need to do to interpret tides is isolate these different periods. Okay. And so what I'm going to show you next is how we might use these, how we might go about looking for other changes in fluid pressure inside the Earth. In particular, we might be interested in looking for the effects of tectonic forces or signals produced by earthquakes. And many of the biggest signals we see are produced by atmospheric pressure changes and tides. And so we need to subtract these to look for these other signals. So here's one example. On the bottom is that barometric pressure. And these are 1-month periods. And then these 4 curves you see here are water level measured in wells next to the San Andreas Fault in California. On the left is the raw water level data, and on the right is the same data, correct effects of atmospheric pressure and tides. And so here you can see as atmospheric pressure gets low, right, water level goes up, and you can see the very nice tidal signal. Once you remove the effects of tides and atmospheric pressure, you can see that at the time indicated by the vertical dashed line, there's an offset in water level, and this is also the time of a regional earthquake not too far away. Okay. The phase between water level changes and tides is proportional to permeability. And so by monitoring water level in wells continuously, you can also measure permeability continuously, at least on timescales of days. Here we're looking at a 20-year record of water level measured in 2 wells in California. So here we're in Southern California. It doesn't matter in detail where the wells are, but you can see the record of water level in these wells. And if we magnify this little portion, you can see the very nice response of water level to those tides. Okay. Okay. And so in this paper by Jean El-Khoury and others, they look at the relationship between the response of water level to tides over time. On the vertical axis is the phase shift. That was the time between the peak water level and the peak tidal forcing. And they see changes that occur at the time of regional earthquakes. Each one of these vertical dashed lines shows the time of a regional earthquake. The map over here on the right actually shows you where those earthquakes are. And every time after many of these regional earthquakes, you can see an increase in the phase shift. Right? And that phase shift is proportional to the permeability. And so what's plotted next is the change in permeability they infer for those different earthquakes as a function of the magnitude of the ground velocity produced by those earthquakes. And they see a nice correlation. And so the implication here is that the occurrence of earthquakes and the passage of seismic waves is changing permeability. And you will notice that permeability goes up and it gradually decays back to the pre-earthquake value. Yeah?
Is storage property also affected?
Excellent question. So storage property it's harder to determine because you're less sensitive to it. But for some of these responses, there's a hint that storage properties may change.
So all those permanently change
That's right. Yeah. You would have to change storage properties a huge amount as well. And I guess that would also show up in the barometric efficiency if you're changing your storage properties. So there are probably independent measurements you can make that would allow you to separate out whether it's a change in permeability versus a change in storage. So just to summarize, right at the beginning I said we need to understand how solids are coupled to fluids, how fluids are coupled to solids. Right? And then there are three questions we wanted to answer. How are deformation and fluid pressure coupled? They're coupled through the mechanical properties and changes in fluid pressure. How do we couple deformation to fluid flow? We do that by introducing Darcy's equation into the equations for linear poroelasticity. I guess the most important thing today really is that the boundary conditions for your representative elementary volume, if you can define one, do matter. And we may measure these elastic properties, the poroelastic constants, under one set of conditions, but we may want to apply those equations and models under very different conditions, and we would need to use different properties. For example, we might measure these elastic moduli using hydrogeophysical methods, where the conditions may be undrained, but we may want to apply those properties under drain conditions, and the expressions will be different. And so what can we do with this understanding? We can determine rock properties like porosity and compressibility. We can also determine transport properties like permeability.
There was one phenomenon you didn't mention, which is subsidence due to overpumping. Could this be also explained by these sets of equations?
Right, so subsidence can have two parts. There can be a recoverable elastic part that would be perfectly well described by the equations I showed you. Sometimes subsidence is not recoverable if there's a permanent deformation. For example, we're assuming that everything is elastic, right? So you apply a stress, you get a certain deformation, you remove that stress, the deformation comes back. If there's a rearrangement of the particles, that will be a non-recoverable deformation. So there's some limitations to linear poroelasticity, of course, then, right? It applies to small strains, but there's many examples of problems where, in fact, it does a very good description. It provides a very good description. And it's certainly a starting point for allowing you to assess what would be unrecoverable deformation.
For the studies you showed concerning the tidal corrections, did those people use like general tidal parameters or site-specific? And would you say it would be important for this tidal correction to have like a site-specific set of parameters? That's right. The second thing is I wonder about just to get an idea about the order of magnitude. Would you, or these people say that I would have to run my hydrological model with a data set of seismic data to account for the change in permeability, or do you think that's like too small to be accounted for? Or maybe it isn't?
Yeah, many questions. First, for the analyses where people look at tides, there are models that tell you what global tides would be at a given location based on knowing the position of the moon and the sun during their orbit. I guess the site-specific area properties will enter through the poroelastic constants that describe the transformation of those stresses from the tides to the water level. Do you need to worry about changes in permeability caused by earthquakes or other deformation? It depends on the time scales that you're interested in and the magnitude of the signals you're looking at.
Is there a limitation for this analysis in terms of where is your well located? For example, if it is where we talk about that, if it's next to a river that is like super changing, and then the groundwater level is also changing in big orders of magnitude, can you apply this analysis?
Yeah.
Okay, so that's the first question. And my second question is like what you mentioned about the reservoirs and fractures. Are there studies that show if fractures have increased due to dams?
Okay, the first question, everything that happens at Earth's surface causes a deformation. So changes in water level in rivers, change in surface temperature. And so not all wells are suited for looking at tidal and doing a tidal analysis. If you have a very compressible system, for example, you have gas bubbles in your aquifer, then the amplitude of the water level fluctuations are very small. If you're located close to the ocean, there are two contributions to the tides. There are the solid earth tides plus the ocean tide. So you would need a model for ocean tides as well. So there's some settings where it's much easier to do a tidal analysis. And the second question was?
If there are some studies related to
changes in fracturing produced by filling a reservoir. We have geophysical techniques now to monitor mechanical properties of the earth, right? For example, the speed at which seismic waves propagate are sensitive to all these elastic properties. And so if you can monitor continuously seismic velocities, you can document changes in seismic velocities, which you can then try and map onto, as we heard in the previous talk, the fracture density or attributes of fractures. Or in this case, for linear poroelasticity, changes in pore pressure, for example. Yeah. Yeah.
Okay. I have a practical question. You said that for the tidal analysis, we have to isolate the frequencies
Yeah.
of the N2 or N2, the one you use. How do you do this? Because in the Shear's article, they use the Golden filter. In other articles, they're using the Fourier analysis. So which one to choose? Sometimes we're seeing that the amplitude changes a lot.
Depending on how you do it.
So,
Yes. Okay. So this is all very tricky. I have only personally used this code called BayTAP, which stands for Bayesian Tidal Analysis Program. But typically, you pick a window over which you're going to do the analysis because you'd like to have as many oscillations as possible to do that correlation. And it seems that typically about 30 days of data are optimal. So that also limits your temporal resolution of documenting changes, that you can get an average over a 30-day time period. And then you have a moving window that simply moves through the time series. But it is very important to separate out those different signals because you can have spectral leakage of one signal into another and then see artifacts that arise from that. It seems like the phase shift is jumping around. So in practice, I think what most people do is they change the time period and look to make sure they're getting stable results.
John?
Still holding within the linear framework, anisotropy would seem to accentuate pressure exactly on the lines where failure would be expected. So how important is anisotropy to some of the injection failures that we see?
Probably almost everything, in the sense that the anisotropy of permeability is going to control where fluids or pressure are migrating and moving. But locally, the failure conditions may still be described reasonably well by linear poroelasticity, just at a smaller scale. But I don't know. But the Earth is for sure anisotropic. And yeah.
I was wondering if we have in fractures channelized flow, so just part of the fracture is flowing. Could these tidal effects affect the pattern, where the channel will be?
Yes. If you're interested in how tides affect fractures, the geometry is more complicated. There's an orientation of the fracture relative to the tidal strains. And so you need to know the orientation of your fracture relative to those stresses. But beyond that, I think the similar idea is that you're expanding or contracting something, and that will change fluid pressure matters. Olivier?
Yeah, I have a similar question about, because usually in fractured system you have borehole flow and you have some, so that the water level variation have a kind of mean between interacting head in the fracture, and so you derive finally a kind of effective parameters for your measure, no?
I think that's right. So the tidal analysis I showed you is a measurement of effective properties over some spatial scale. And that spatial scale, in fact, depends on that thing I called alpha. It's basically the length scale over which those pore pressures migrate into the aquifer. But maybe at the very beginning, I showed you this example. of a seismic waves coming from an earthquake 3,000 kilometers away, and then water level in the well. And so the geometry there's similar, it's a similar problem to the tidal problem we talked about. We have an oscillatory deformation, and water's going in and out of the well. But here the geometry is a little bit different. We assume that from the camera we put down the well, we see there are fractures that intersect the well. So now we can solve the same type of problem, but we have a fracture surrounded by a porous material. The porous material is compressing and uncompressing, forcing fluid in and out of the fracture that is intersecting the well. And so we can obtain, in fact, a different solution for the amplitude of pressure fluctuations. And that's what I plot down here. The difference now is the horizontal axis is period, or 1 over the frequency. And the black curve is the expected response, and the points are the measurements. So provided you think you know what the geometry is, whether you have fractures or just a uniform porous material, you can try and couple those types of problems to take the next step.